whenever you solve a material balance, you have to have a basis. Normally, the basis is the flow rate that is given, or the amount that is given normally. But if there's no flow rate given, then you can assume one value, and that is always usually 100 mole, or for example 100 kilogram per second. It's better to use 100 because it's the safe assumption to use. Okay? Once you have assume a basis, or you get a basis, then draw your block diagram. You need to draw your block diagram and label whatever information is given. Whatever is not given, then give it a symbol. Normally for mole, for example, mole fraction, you will use X or Y, and for flow rate, maybe you just use any capital letter. If it's liquid, for example, you use L. If it's gas, maybe you use G. You can assign any nomenclature that you prefer. Once you have draw your block diagram, now you need to look at the system. Is it open system? Is it closed system? If it's an open system, write down the equation for it. And then, if you know that it's an open system, you need enthalpies. So if you need enthalpies, look at the system itself. Is there any available data that you can use? For example, from the appendix. If it's steam table, obviously. If it's steam, if it's water, obviously you can get it from the steam table. But if it's other than that, sometimes you have the data available, but sometimes you don't. So if you don't, then you have to calculate it. That is the part that we're going to cover in chapter 8. But most of the time, you can easily get it tabulated. Okay, once you have done that, before you can solve your energy balance, you need to have a reference state. We have looked at some reference state. It depends on where you get your data from. If it's from the steam table, then your reference state has to be similar as that of the steam table. It has to be, because wherever you get your data from, then your reference state must be the same as that data, the source of the data. So it must be the same. Unless if you are calculating your own value using enthalpy, for example, then you can choose any reference state you prefer. But there's a certain rule also. If in order to make life easier, then there's a certain rules if you want to how to choose your reference state, which we will cover in chapter 8. Once you have done that, you can start to solve your energy balance. And we have done some examples. The energy balance, they're not that difficult. They're just based on the type of the system, the equation that you're going to use. Okay, guys, so let's proceed to an example. I'm going to look at example 762. Let's see whether I can stop sharing first, so that I can go to example 762. Let me go to my PowerPoint. You have your textbook with you, or if you have the internet, we're going to look at example 762. And that's, sorry? Did you say something? Okay, let me, where is my, okay, share. I need to share my PowerPoint. This is example 763, not 2. I mean, I'm going to look at 762, not 3. Let me go to the next slide. Yeah, this is 761, sorry, 761, not 2, 761. If you look at this example, let's go through the equation. You have 2 streams of water, going to mix it up. We have stream 1 and stream 2. You're going to mix it up so that you will produce another stream, which is the outlet stream, having a pressure of 17 bar absolute. And that stream will be sent to a boiler. Now, what the existing stream, the stream that will be sent to the boiler, will pass through a 6 centimeter diameter pipe. But the 2 streams that are fed to the mixer, there's no specification of the size of the pipe. So we're going to assume that there is no kinetic energy there. So which is stated here. Neglect the kinetic energies of the liquid inlet stream. So if there's no mention at all about the size of the pipe, the diameter of the pipe, that means you can assume that there is no kinetic energy. Okay, so let's continue. What do you need to calculate? You need to calculate the required heat input to the boiler in kilojoules per minute if the imaging stream is saturated. Saturated, that means your 17 bar is saturated steam. Okay, so if you draw the diagram, that's how it looks like. This is from the textbook. You have stream number 1, 120 kilogram per minute at 30 degrees C, 120 kilogram per minute of water at 30 degrees C. Over here is listed already the enthalpy. I will show you guys how to get that value. Okay, stream number 2 is coming in at 175 kilogram per minute at a temperature of 65 degrees C. Over here, 175, and the temperature, again, the enthalpy is listed here. We will look at the stream table, how to get that value. And the third stream, which is the outlet stream, this is your outlet stream. The value of the meter balance of the stream, we would solve that using the meter balance, and that's the pressure. It's stated in the question that it is saturated, so that is saturated. And the enthalpy, we will look at how this value is obtained and the size of the pipe. So I'm going to stop using my iPad. So I'm going to stop sharing this slide. I'm going to share you guys my iPad. Let's see. Okay. Okay. Let's see whether I can make it bigger. Oops. I keep on doing that. Okay, that's good enough. Let's draw the what do we have to do first, you guys? You tell me what we have to do.
Basis.
Basis. Okay. What basis are you going to use?
120 kilogram per hour.
Okay, we can. You have two stream coming in. You can choose either one. So since you specified 120 kilogram per minute, you need to specify per minute. You need to mention that it is at 30 degrees C. Okay, that is your basis. You can choose the other stream if you prefer. You can choose either one. Okay, because the outlet stream you don't have the mass flow rate, so we normally don't use the stream that doesn't have a mass flow rate as your basis. You will choose a basis that has a given flow rate. Okay? So this is one of the basis that you can use. The other one, it will be the second stream, the input stream. Okay, that's the basis. Next, what are we supposed to do? Anybody?
The diagram, that's it.
Okay, let's draw the diagram. Okay, you need to draw your block diagram. Okay, well, I have here the input stream, 120 kilogram per minute. It is specified that it's water. So let's put water there, but we will check whether it's liquid water or whether it's steam. Okay, it's specified that it's water, but we're not sure. Is it liquid water or is it steam? So the temperature coming in is 30 degrees C. Anything else specified? No, just 30. We have the second stream. The second stream is 175 kilogram per minute. The temperature is given. Again, it's mentioned water, but then could be what liquid, could be steam. We don't know. And the outlet, since we don't have the mass flow rate, let's put a symbol for it. Let's say this one is M2. That will be M3. And this is equal to M1. I don't have enough space, so I'm writing inside the block. That's kilogram per minute. Okay, the temperature is not given, but it is mentioned that it is saturated steam. In the question, it says it is saturated steam at a pressure of 17 bar. That's absolute. Yep. What else is given? No, that's it. That's the only information that we have. So next, oh yes, forgot about the 6 centimeter ID, the diameter of your pipe. Okay. So we need to calculate Q that is going to be put into the system. What is the Q? Okay, we have done the block diagram. We have specified we have denoted the unknown flow rate as m.3, the flow rate of the outlet stream. So what else to do next?
Material balance and
Material balance. Okay. Okay, let's do the material balance. You guys have your diagram there. I don't my diagram I can look at it. Okay, that's my diagram. Okay, so material balance. You have, if you look at here, M1. How to get the equation, please?
M1 plus M2
M1 plus M2.
Equals?
M3.
Okay. M1 plus M2 plus M3. Oh, it's the dot. Okay. So M1 just now is supposed to be 120. M2, what was it just now? Somebody give me the value. 125.
175.
Yeah, 175. 175 is equals to M3. So if you total it up, it should come up to be 295 kilogram per minute. So now you already have your material balance. Okay, let me tidy that up. Okay, per minute. Okay, that is your third stream, the outlet stream. Now let's look at we need to look at the enthalpies. Why do we need to look at enthalpies? Before that, what's the next step?
We have to identify the system and
Okay,
then come up with the equation.
Okay, what system are we looking at?
Open system.
Open system. Okay. Okay, give me the equation then.
Change in H,
Change in enthalpy.
enthalpy, plus change in kinetic energy.
Sorry, I got that wrong. What did I just wrote?
Change in enthalpy, no? Yeah.
Yeah, not the internal energy. Okay, next.
Plus change in kinetic energy.
Okay, kinetic energy.
Potential.
Potential energy, change in potential energy.
Equal to Q plus W.
Okay, remember that this is a flow rate. So there's a shaft work, there's a subscript S there. And we are looking at open system. So now that you know it's an open system, before you can proceed, what do you need to specify?
Reference state.
Reference state, yes. So what is going to be your reference state? Yeah. Your reference state.
The one on the table.
The one from table. What table?
Saturated waters.
Okay, you're looking at steam table. You know that you're dealing with water. You know that you're dealing with steam. So you know that you're going to get your enthalpies from the steam table. So what is the reference state of the steam table? Anybody? We did mention it last few lectures. What is the reference state of steam table?
Wait.
Sorry?
Just a second.
Can't catch you. What did you say?
Just a second. Just a second.
Just a second. Okay. I was trying to figure out what did you say just now. Okay.
It is
0.
0. Yeah, go ahead.
0.01 and 0.00611.
Okay. What are these values?
The temperature and pressure.
Okay, 0.01 degrees C. And then pressure is equal to 0.00611. What's the unit?
Bar.
Bar. And what is the state?
First step.
Liquid water, isn't it? It's liquid water, isn't it?
Yes.
That is for liquid water. Okay. So that's your reference state. Now, I'm going to show you guys the slide. Let's see. Let's look at our diagram. We have water mentioned coming in at 30 degrees C, and the other water coming in 65 degrees C. There's no mention at all about the pressure, isn't it?
Yes.
Okay, but the outlet stream, there's a mention of the pressure, 17 bar, absolute. It is saturated. So look up your saturated steam at a pressure of 17 bar. And what is the enthalpy for that stream at 17 bar? So I'm going to unshare my, okay, I'm going to unshare this. Okay, I'm going to share you guys my PowerPoint. Or I have the steam table. Where is my steam table? Okay, this is my steam table from the appendix. Let's see, 17 bar. Okay, that's not 17 bar. That is temperature. That is temperature in 17 bar. Can you find anything 17 bar? You have 14.69. That is absolute pressure. Where is it? That's kilopascal. That's kilopascal. Okay. So where else? Let's look at a different table. I have it on in my PowerPoint. I have the table in my PowerPoint. So let's see. Can you see 17 bar?
Yes, yes.
That's there, isn't it? I'm not sure whether I have, let's scribble.
It is 871.8.
Okay, that's, let's see. You mentioned that's 17 bar. Yeah, that's 17 bar. Where is the enthalpy? That's the enthalpy. So it's mentioned that it is at 17 bar. It is saturated steam. So you're not going to use that value for water. You're going to use for steam. So let's see. One, that's it. 2793.4, isn't it? What did you mention just now? Somebody gave me a value just now. You mentioned 871, is it?
Yes.
You got it wrong. You cannot use this value. Why? Because that's water. The question states that the imaging steam is saturated. So you have to use steam at that value, the enthalpy 2793.4, which is given here. Okay? So do not use water. Why? Because it's steam. Okay. For stream number 1 and number 2, it specified the temperature. For stream number 1, 30 degrees C. So look at 30 degrees C. So that's 30. So we're going to look at the enthalpy, which is that of water. Even though it's specified that it is water, you can double check. If the pressure is given, you can double check because you need to check whether the temperature is saturated, whether the temperature is above or below that saturated temperature. But in this case, the pressure is not given, only the temperature. So obviously it is liquid water. So that is 127. That is the enthalpy that you're going to use. So that's the enthalpy here. Okay. So for 65, unfortunately, you don't have the exact value at 65. You only have 64 and 66. So you need to interpolate. After you have interpolated, you will get that value, 271.9. You can try to get that value. So let's, that is liquid water. So 66, that value, and 64, that value. Interpolate, you see whether you get the same value as 271.9. So let's do the interpolation. Whether you can get it, I did not get 271.9. Somebody check whether you can get 271.9 because I got a different value when I did it.
I got
What did you get?
72.05.
Yes, 72.05. Yeah, that's what the same as what I got. Yes. The rest of you guys, did you try? Did you manage to get 272.05 or did you manage to get 271.9? Just like the author. The rest of you guys try. Somebody managed to get it the same as me, 272.05. How about the rest of you guys? Still doing it? Wow. Anybody already besides Let's see who just now. I need to see who you are just now. Let's see.
Doctor,
Yes,
I got 272.05.
yes, the same. Aiman, you managed to get the same as me, and let me see. Just now, I know you are the from Subhakit. Subhakit, is it how to
Yes.
pronounce your name?
Yes, yes, yes.
Yeah. Okay. Your I could hardly hear your.
Doctor,
Yes.
for me, I got 2.15.
That's wrong. That's wrong. Definitely wrong. Recheck your calculation.
Doctor, the answer 272.05.
Yes. Do
Okay.
you get it?
Yes, I get it.
Good. Good, Nabila. You managed to get the same as the rest of us, except for whoever did not get the same value. That means 272.05. That means you need to recheck your calculation. Okay, so let's unshare this. We're going to look at our calculation again using my iPad. This is quite a bit, it's a bit not the norm because we are using online. So I'm going to write down the enthalpy that we managed to get. Let's see. Let's write it down because it's easier once you have everything written down. That value is supposed to be, hold on, let me see the value, 125.7. The unit is going to be the same as that of the steam table, kilojoules per kilogram. Okay, the give it subscript of 1 because we denoted that stream as stream number 1. This subscript number 2, and we managed to get 272.05. I don't have enough space to write the unit. And lastly, for the outlet stream, we have a value of 2793 kilojoules per kilogram. Okay, everything is there. Let's look at our equation. We have our equation over here. Okay. Our energy balance equation. What else can be eliminated from that open system equation? Anything that can, make it simplified, easier, less calculation.
Potential.
Potential, okay. There's no
Shaft
change
work.
in energy.
Shaft work.
Shaft work because there's no turbine, there's no pump. It's just mixing. So
And
now,
Kinetic. Okay.
inlet kinetic energy.
oh no, you can't cancel that.
Inlet.
Because it says in the equation.
Inlet only.
Only the two inlet stream you ignore the kinetic energy, but the outlet stream there's a mention of the size of the diameter. So if there's a mention of the size of the diameter, that means you got to calculate the velocity of that stream. And if there's velocity, definitely kinetic energy has to be calculated. Okay. What else? Is there mention of you're supposed to calculate heat? So heat is the unknown. So let's rewrite the equation. You have change of enthalpy is equals to, you're looking at open system. So the equation will be out minus in. Okay, your flow rate is in mass and your specific enthalpy. That's your the inlet outlet, and this is for the inlet stream. Okay, so I'm going to write that first, and next for the kinetic energy is equals to half m u square, change of u square out minus u square in. Okay, that's your kinetic energy. But it's already specified that in is going to be ignored, so you're going to ignore that part for the inlet stream. So that's your kinetic energy. So now let's do the potential energy first, since we already have the, sorry, not potential energy, the enthalpy, since we already have the enthalpy. We already have the enthalpy, so next go to the next slide. I'm going to do it in a table form. Yeah. As usual. How many streams do we have? We have 3 streams. But we're not going to draw all, we're not going to write 3 of them. So we're going to say water, This is water. Let's see. This is quite difficult because there's 3 streams actually. Okay, let's put 3 of them all together. This is in water. And this is steam. Then we have 2 streams coming in and 1 stream going out. So this is your mass in. I'm not going to write the unit because, okay, we need to write the unit actually. Do not skip it. It's kilogram not per minute. I need to write quite small because I don't think I have enough space. Let me try to squeeze everything in. Let's see. That is in kilojoules per kilogram. Okay, that's in. And in, that's the mass out. OUT, kilogram per minute. See, I don't have enough space here. Okay, that's out. I don't have enough space to write the unit. Okay, that's good enough. Okay, the water coming in, you have 2 streams. Let's write the values in that. Let's fill up the table. That's 120 kilogram per minute. The other stream coming in, 100 and let me look at my 175. There's no steam coming in. The steam coming out, you already calculated the flow rate using the material balance. That's 295. Okay, let's look at the values that we have noted down the enthalpies before that. You have the enthalpies here. The enthalpy for the stream coming in, 125.7 for the first stream. And for the second stream, 272.05. And the outlet, the enthalpy is 2793. So let's put in that values inside our table. The first value is 125.7. The second value we got after interpolation, 272.05. There's no outlet stream here for the water. The outlet stream, the enthalpy is 2793, which we got from the steam table. So now, using the equation, delta H is equals to out mass multiplied by the specific enthalpy minus in mass the specific enthalpy. So how to do it? Give me the values, guys, from the table. Anybody? What is this is out. Oh dear.
295 times 2793.
Okay, 295. Your unit is kilogram per minute. Okay, I'm not going to write the unit. Why? Because I don't have enough space. So I'm going to write just the values. 2793. Okay, minus. Now you have 2 streams coming in. So I'm going to put a bracket around it. The 2 streams coming in, get the product, please. Anybody? Nobody? Okay, let's do it. You guys are not going to speak to me. I'm going to just continue with the calculation. Plus the other stream. Okay, that's close the bracket. So what's the answer, please? And now I'm going to write down the unit. The unit is supposed to be kilogram per minute for the mass flow rate, and the enthalpy is kilojoules per kilogram. So I'm going to cancel that. I'm going to have my unit of kilojoules per minute. Oops. So what's the answer? Anybody? Did you get the same as the textbook? What did the textbook manage to get? 7.61 times 10 to the power of 5. Is it the same?
Yes, same.
Yes.
7.61 times 10 to the power of 5. Okay. That's done. That's the change in enthalpies. Now you need to look at the change in the kinetic energy. We have the kinetic energy. If you look at the second slide, we have the change in kinetic energy. So that's what we're going to calculate next. Yeah, the change in the kinetic energy. Oops. Okay. Why did I just write there without the minus sign? Because we already know that from this equation, the bottom equation, the inlet velocity, we're going to ignore it. Because it's mentioned in the equation that you can ignore the two inlets kinetic energy. So you only have the outlet velocity that you need to calculate. Okay, so let's go to our slide. What is given? You are given the internal diameter of 6 centimeter. You have the mass flow rate of that stream 295 kilogram per minute. Yeah. So if you know that, do you think you can calculate the velocity? This is calculate. This is not 2.
Yes.
It should,
Yes.
okay, guys, I need to change my symbol here. I cannot use 2. The reason I cannot use 2 because remember number 2 is the stream that is coming in. Stream number 2 is stream number the one that is coming in, isn't it?
Oh,
So what
yes.
symbol? So over here I have out. Over here I have out. I have over here out. So it should be, what is the symbol? Out or what?
3.
3. Okay. Should be 3. This one should be 3. That should be 3. Yeah. Or out, whichever you prefer. So now, how to get your velocity? Let me erase that. The unit of velocity should be in meter per second. What you have is kilogram per minute. You have your mass flow rate. That's number 3. Oh dear. Oh dear. Hold on. Where I need to find my, hold on. Guys, I seem to lost my calculation. Where is it? Hold on. That is not it. That is not it. Hold on, I lost my calculation. Oh dear. Okay, that's it. That should be 3, not S. Yeah, that's 3 kilogram per minute. How are you going to arrive to meter per second? You know you're going to change the minute to second, that's obvious. So how to get rid of the kilogram?
Use the
The
density.
conversion.
Density, okay. So you need to multiply or divide the density?
Divide.
Divide.
Okay, divide. Because the unit of density is kilogram per meter cubic. But once you manage to get rid of that, but you still have meter cubic, so what else do you need to get rid of?
Divide by area.
So area.
The cross-sectional area, meter square.
Yes.
Yeah, so cancel that, you can end up with meter per minute, but you can change the minute to second. So the actual equation will be something like this. M3 divide by the density of water and the cross-sectional area of your pipe. Okay, the cross-sectional area of your pipe is going to be pi over 4 diameter square. Since you already have the diameter, pi over 4, my diameter is 6 centimeter. Let me erase that. Okay. 6 times 10 to the power of minus 2, because it's in meter, square it. So you should be able to get your area. I'm not sure what the area is. It given in your textbook? Yes, it is given.
2.8274.
2.8274.
2.8274. 3 times 10 to the power of negative 3.
27. Okay, times 10 to the power of negative 3 meter square. Thank you. Yeah, thank you, Sulaiman. So that's the cross-sectional area. Your density of water, anybody?
1,000 kilogram.
1,000.
1,000. That's it. Yes, 1,000. So now your velocity is going to be your mass flow rate 295. I'm not going to write the unit because we already know that the unit is over there. I'm not going to write it because I don't have enough space. Okay, but if I want to write it, I think I can do it. Okay, let's put in the unit. That's kilogram per minute. I need to change the minute. 1 minute, 60 seconds. My density, oh dear, that's a very long number. That's kilogram per meter cubic. And I need to divide it by the cross-sectional area. The cross-sectional area, I don't have enough space to write the cross-sectional area. That's why I don't want to write the unit just now. So I'm going to erase this. You guys know what to do with the unit because if I write the unit, I don't have enough space. You continue with your calculation with the unit, but I'm not going to because I don't have enough space. Okay, I know I need to change 1 minute to 60 seconds. Okay, I have the cross-sectional, the diameter and the cross-sectional area. That is the cross-sectional area. The density, sorry. I need to get the density. Okay. That is meter cubic. That's the cross-sectional area. So what's the answer? The velocity should be 202, is it?
Yeah.
202. Is it? Meter per second?
Yes,
Double check, please.
Yes, that's correct.
Yes, good. Yes. Somebody, okay. So that's done. So now what you have to do is put that value inside your kinetic energy equation, which is this equation, equals to half. The mass flow rate should be that mass flow rate of which stream?
The exits are the product.
The exit stream, isn't it?
Yeah.
Yeah.
Yes.
Okay, so that's 295 times by the velocity just now 202, but you know that unit has to be converted to the same unit as your enthalpy. Your unit of your enthalpy just now, when we did that calculation, is kilojoules per minute. This unit is kilojoules per minute, so that means your the kinetic energy should also have the same unit as kilojoules per minute. But if you multiply just the mass with the velocity, you're not going to get kilojoules per minute. So you need to convert it, whatever unit you have over there, to kilojoules per minute. So let's see whether, let's do it. I'm going to use a div. Okay, that's in. I need to add up more page. Hold on. Let me add up one more extra page. Okay. I don't want this. Okay, that's it. I'm going to erase the whole thing. Okay. So now we have this now, the kinetic energy is equals to the value of half times by the flow rate 293 or 95, 295 kilogram per minute, and you multiply it with the velocity meter per second. So how are you going to get that into kilojoules per minute?
1 Newton
Okay, 1 Newton.
equal to 1 kilogram per times meter per second square.
Okay, 1 Newton equals 1 kilogram times by meter per second square. Okay, we cancel the kilogram. We cancel. Again?
The velocity is meter cubic per second cubic. Meter square per second square.
Okay, 1 Newton is equals to 1. Sorry?
I mean the velocity 202.
Okay. Thank you. Okay, yeah. Because that is square, isn't it? So
Yes.
this has to be square. Is that right?
Yes.
Do I need to square it? Yeah. Okay, I need to square it. Because if you look at the equation over here, it has to be square. Okay, so let's erase this part. Okay, so you have the square there. You have the square there. So don't forget about the square to the power of 2. Okay. So let's go to our slide. Okay, now the last page. You have need to square it, so you cancel that square, the second square. Now you need to change. Sorry,
1 Newton, 1000 Newton times meter.
1 Newton is equal to
1 Newton times meter equal to 1 kilojoule. 1000 Newton times meter equal to 1 kilojoules.
1000 Newton.
Right? 1 kilojoule here, up.
1 kilojoules. Here is 1
Yes.
kilojoules.
Down,
Okay.
right? 1000 Newton times meter.
Okay, hold on. That's kilojoules, or is it per second? Kilojoules per second, is it?
No.
No.
Kilojoule per, down you write 1000 Newton times meter.
1000 Newton. 1 kilojoules, is it?
Yes, Newton
Got it.
times meter.
Times meter.
Yes.
Newton time by meter. Okay, I don't have enough space to write down. Okay, let's write down. 10 to the power of 3 Newton time by meter. Okay, is that it?
Yes.
Is that it? Okay, meter square, cancel that. You have Newton, you cancel the Newton. And now you have kilojoules per minute. Yeah, that's it. Thank you. So what's the final value for your change in kinetic energy? Is it the same as the textbook, which is 6.02 times 10 to the power of 3? Is it the same? Double check, please. Is that the answer that you managed to get after doing the calculation? Is it, guys? 293 divided by 295, sorry, 295 divided by 2 times by 202 square, and then divide by 1000.
I got 5.97 times 10 to the 3.
Okay. The rest of you guys? You get 5.97, the same as, who's the one that's now who spoke?
Ayman.
Ayman, okay, thank you. I cannot recognize you guys based on your voice. I'm not used yet to your voice. I do apologize about that. It's very difficult not face to face. I have, if we come face to face, definitely I will recognize everyone. Okay, did any of you guys get the same answer as Ayman? 5.97 times 10 to the power of 3? How about
Yes,
you,
doctor, is
Ayman?
correct. Yes,
Good.
yes.
Yes, thank you. Okay. So definitely that answer is different from the solution in the textbook. So now the final equation. Let's look at the final equation. The final equation that we're supposed to calculate is Q. We're supposed to get Q from this open system equation. Okay, from this equation, we're supposed to calculate Q. And Q is equal to the change in enthalpy plus the change in kinetic energy. So let's solve for Q, the heat. Change in enthalpy plus change in kinetic energy. So we managed to get the enthalpy just now. The enthalpy is, where is the enthalpy?
Doctor,
Yes,
sorry to interrupt, Doctor. May I know, is it 295 or 293 in the kinetic energy equation?
295. 295.
295, because I got 6.02, same as the book.
Okay. Just now I wrote this 3, but I changed it to 5, remember? 295. Yeah. The guys, when you got 5.97, was it based on 295 or was based on 293?
293.
Okay, sorry. I did mention that it's supposed to be 295. Sorry, it's supposed to be 6.02 then. Thank you. Again, who's the one speaking just now?
You're welcome, Doctor.
And who are you?
Gan.
Okay, Jin.
Gan.
Gan.
You can
Okay,
call me
Gan.
Gan, yeah.
Okay, Gan. Okay, thank you. Okay, guys, I wrote this wrongly just now, 293, but I did correct, mention it, 295. I correct it, but it looked like 293. Sorry about that. Okay, 602. So let's continue with our calculation. Thank you, Gan. So our potential, change in enthalpy just now 761. This is the change. This is the change in enthalpy. 761 times 10 power 5. Yeah. So 7.61 times 10 to the power 5 plus the kinetic energy. Kinetic energy we got. Oh, it's already up there. 6.02 times 10 to the power 3. So you plus it up, you sum it up. If we look at the textbook, the answer is 7.67 times 10 to the power of 5 kilojoules per minute. That's the final answer, which is the amount of heat that is going to be supplied to the stream in order to produce your steam. This is not a mixer, actually it's a boiler. You're going to boil the two stream coming in, and you're going to have your saturated steam as the outlet stream. So that's the amount of heat that you need to supply in order to get your saturated steam at a pressure of 17 bar, which is a temperature of 204 degrees C. So any questions? Any questions? Sorry
No, it's
about
clear.
this now, about 295. Yes, Sulaiman.
Yeah, it's clear. It's clear.
Yeah, good. Yeah, good. I already recognize your voice, Sulaiman.
Doctor,
At least, yes. Ayman, is
may
that you?
I ask you? Omar,
Yes?
Omar.
Omar, okay.
At the beginning, for the enthalpies, okay? For the two stream inlet, we have the 30 Celsius and 65 Celsius.
Yes.
So we make an assumption is it is an saturation in the saturation.
It is, we are going to assume that it is water, completely water. It's not a mixture of water and steam. It's not a mixture of water and vapor. It's mentioned that it is water because we are given the temperature. So we're going to assume that it is saturated water, liquid water, saturated liquid water.
Okay, doctor, thank you.
Okay, thank you. Any other questions?
So, doctor, if it's compressed liquid, it's gonna have the same value as saturated water.
Sorry, Ayman, can you repeat that again?
I mean, if the state is compressed liquid, the value of enthalpy going to be the same as saturated water.
Compressed liquid. If you mention compressed, that means you have to mention the pressure. But the pressure is not given here. So sometimes compressed liquid could be super cold liquid. It could be saturated, it could be super cold liquid. That means it's below the saturated temperature. So you need to have the pressure in order to verify, is it saturated or is it super cold? But since the pressure is not given, then we're going to assume that it's saturated water. All right.
Yeah, thank you.
You're welcome. Any other questions?
Doctor,
Yes.
for the earlier part, for the enthalpy of the inlet, I got 271.9 if I use the pressure table, not the temperature table.
Oh, you are referring to the 30 degrees C, is it?
Yes, 30 degrees C and 65.
You are using the pressure.
Pressure table, yes.
Don't use the pressure table.
Okay, so
Why? Because the pressure is not given in the question.
Oh, okay.
Okay, the temperature is given. If you're looking at liquid, liquid is more affected by temperature than pressure because it's incompressible.
Okay, all right.
Okay, so look at the temperature, but not at the pressure for liquid. But if you're looking at gas, then yes, gases are affected by the pressure. That's why your steam, when you look at the outlet stream, the saturated steam, it is specified, the pressure is given. Okay? But because it is saturated, you don't need the pressure, the temperature. You, with just one value, you can get the enthalpy because the pressure will give you the value of the temperature because it's saturated.
Okay.
Okay. Any other questions? Yes. Thank you, Gan. Any other questions? Seems to have only these 4 students communicating with me. What happened to the rest? Are you online or are you not online? Do you understand or do you don't understand? There's no response at all. So far, every time, good. And who's the one speaking? Who's the one speaking? Arif. Come on, I don't have my your name display here. Okay, somehow I don't have your name display here. Okay, good. Everybody clear on that example? Guys?
Oh yeah, doctor.
Good. Okay.
Yes,
Okay, good. Tag 5, we will continue with the second example after this. Tag 5, so be back here by 3 or what? 3 or 1? 5 minutes? 3 or 1? Okay, guys? Okay, tag 5, please.
Okay.
Okay, thank you.